Josh, thank you. Welcome back. Thank you for coming back. Monday night, I'm pretty pumped up. Maths 2504. Okay. So I'd just like to start with just always looking at the timetable, looking at what we've done, what we're going to go through for this next bit. So aim for this week is we'll finish off Unit 1 in this lecture, and then we'll start on Unit 2. Unit 1's just this intro thing. We talk a little bit about why we're doing this, show a couple of interesting problems. Hopefully they're interesting. Who found the square root one interesting? Interesting, not interesting? I have to make it more exciting, more dancing or something. Yeah, so that's what we went through last time. This time we'll go through two more little, semi-useful problems that motivate everything. Unit 2 is going to get a bit more algorithmic, which is cool. And we're going to start looking at analysis of algorithms, and we're going to talk a bit more about some more deep data structures that will be useful for you. So like at the moment, we've looked at basically ints, and I've sort of waved my hands at floats. Natural numbers, real numbers, a model for those things on a computer, and kind of the weird things that you're going to get when you start using these things for real. And these things are real. Some of the stuff I've talked to you about already do happen, and you do have to worry about to me regularly. So particularly, for ints, that overflow property, where if you start adding and adding and adding, and you think they're going to add up forever, and then all of a sudden they go back under the bottom, that will hit you in strange ways, in places you'll never expect. Yeah, so the next bit, though, is going to be starting to look at sorting as a motivator for this algorithmic style of thinking. I'm going to say it like 18 times. It's like, I don't actually care that much about sorting and that you guys understand sorting. I care that you think about the performance of sorting and how you might make it better and that sort of thinking. So when I was talking through Unit 1, I sort of said, addition. If you're thinking about that adder circuit where it's got like n bits and you've got order n to do adding and order n squared to do multiplication. That sort of pattern of how algorithmic complexity grows with the type of problem you've got and how you might fight it. That's like, if you're doing algorithmic software development, which is, if you're a maths background, that's a place you will probably land. That style of thinking about the asymptotics of complexity is like a really big deal and something you can do well. It's simpler than it sounds as well. Like there's a couple of tricks, you build up a bag of tricks over time that you can start applying to different problems, because there's this similarity in patterns of design for these types of problems. Okay. Yeah, section 3, we'll go back. I think I kept saying in Unit 2 we'll do floats, but Unit 3 is where we're really going to talk about floats when we're talking about numerics. That's where we're going. Okay, in terms of, I'll just ask again, has everyone got a partner for big homework yet? Or if you don't, put your hand up. And anyone not have a partner? Anyone else? You guys, you should probably talk to each other because it's getting slim pickings by the end. So yeah, everyone made a start on the homework? Anyone, how's it going so far for most people? Yeah. Any of it horrible? Anyone, like, I'm happy, like, in the break or even during this, if you're really stuck, I'm happy to go over some of that stuff during the lectures. Like we can take a little break and talk about that stuff as we go through. Just give me a heads up so I can get my head in the right spot. Like maybe in the break, if you want to talk about a particular question, we can motivate some of the lecture material with that, because I understand we haven't gotten to all this stuff you're trying to do yet, so teleporting a bit into the future might help you with that, some of that stuff. Okay, cool. I think I'm happy with that. Unit 1, where are we up to? I'm pretty sure we got up to finishing talking about square roots. So did a hello world, showed a bit of lowered code. This guy will come back up again. I think I skipped over this about an alternative data type for integers. That'll come up in this next one we're going to talk about. I think I brushed over that and went, yeah, we'll do that next. This thing here of this sort of like mysterious algorithm that popped up 2000 years ago, this recursive algorithm. We're going to talk a little bit more about recursion in this episode of the lectures. Recursion is a pretty natural way to set up problems in mathematics. Like a lot of the ways you would generate an algorithm from the definitions in maths naturally end up with a recursive implementation. We didn't do a recursive implementation, we just iterated. So like we started with the first guess and went all the way through. A little trick we can do is recursion, where you actually call the function itself from within the function. That's it's kind of a, if you haven't done this stuff before, that can be a bit of a flip in your head to think that way, that that's okay to do, but it is totally okay to do. In terms of Julia syntax, I think we've given you, I told you this guy is like optional named arguments. If you want to have something in your code that's like, most of the time I'm not going to bother setting this variable, but I want the opportunity to pass it in later on. You can put one of these named arguments where you put semicolon, then a guess for what this variable is going to be. So if you call this without setting these optional arguments, they'll have a value defined. That's cool. So square root, basically hiding underneath all this stuff is Newton's method, which is calculus. You do a linearization of a nonlinear function around a point, solve for when the linearization will be equal to 0. That's your next guess. Go back to the function at that point, linearize around that point, solve for 0, again, again, again. If you with those points we said last time, which maybe you can remember, if you have a good enough first guess, your function's not too pathological, your derivatives are not too weird, you know, going to 0, because you're going to be dividing by 0 with this guy on this iteration, so that's not a good thing to happen. You should iterate down to a good solution. This is ubiquitous way of solving lots of problems in maths. So like, and the trick is like, there's lots of tricks about making this faster, convergence faster. I gave an example of this in the wild, which isn't for the square root, it's for the reciprocal of a square root, a kind of infamous implementation. I don't want you to code like this, but it's a nice example of some weird stuff that you might see when you're out there. And basically, I don't care too much about you understanding this. I just want you to have seen it. Is that this whole chunk of code is doing a weird first guess that's really, really good. And then you do one Newton iteration and you're at the end. Cool. Did anyone have any questions about that first part before I forge on? Everyone happy? Ah, good, good. You can shout out, interrupt me if I'm saying stuff wrong as well. Just, we'll get there. Okay, so this one is factorial. So this, you know, factorial, what's the definition of factorial? Anyone want to say what it is? Taking factorial of a number. Yep.
Is there by summation from the number to 0 or 1 and minus 1?
Yeah, so the product from iterative product. So if you're going to go like the factorial of 10, which we can just do, I'll just get this guy across here. I didn't start Julia, which is annoying. Okay. So the easiest way to do this is you go, if you go like, I need to take a factorial, let's see if the standard library implements this for me. And then I've got nothing to do. So start typing fact, press. Has anyone worked out pressing tab to finish the function name for you? So if I go FACT, I can press tab and it will finish and go factorial. So if you're trying to search through this thing, it's a useful trick. Factorial, I've said help. I don't know how to do this. So do the shift question mark factorial. It'll say, oh, cool. That noise again. It's really awful, isn't it? So factorial of a number n. If n is an integer, factorial is computed as an integer, promoted to at least 64 bits. Oh, cool. Thank you for getting that off. That's awesome. Oh, yeah. That's terrible. No, I can't. I'll just minimize it. If we see, if anyone notices that it's someone's in there pinging this on chat, just let me know. Okay. So promoted to at least 64 bits. And this is like, you've said about this product, it's like, how quickly is that going to grow as n gets big, right? Like pretty quickly, like kind of the worst case of things growing like this. So note that it may overflow. N is not small, but you can use factorial big N to compute the result exactly in arbitrary position. So that's basically like the first bit of this lecture in the help. So you don't need me at all. You just need the help. We're going to go through that though. So if you want to actually do it, factorial of 1 is 1, factorial of 2 is 2. So 1 times 2, that's what you're trying to do. 3 should be 1 times 2 times 3, 6. 24, it's growing really, really quickly. That's this thing in factorial, because it's like every time it gets bigger and bigger multiplicatively. We can calculate this in a variety of strange ways, which we've got in the thing. So I've been glibly doing, 1 plus 2, you can do this for plus as well. So plus is a function. So you can do help plus, and it will give you a bunch of things help for plus. But you notice this strange, say, we call it infix versus prefix notation for functions. For some special functions, you can do them as infix, which means you put them in between the arguments. Most functions you'll call are prefix, where you have the function name, then you put brackets and you put the variables. Any of these infix operators like plus and times, you can also do them as a prefix. So I can go plus 1, 2, and it'll give me 3. I can do the same for times, prefix. I probably showed you this splatting thing. Oh, there's 2 bits here. So setting up an iterator, you've probably all done this and not thought about it. When you actually do this, I go 1 to 10. It doesn't actually make an array with 1 to 10 in it. It just makes an iterator. So if we think about how much memory a computer is going to use, you often don't care about making this intermediate thing. You just want a thing that will pop the values out every time I ask for a new one. So this thing, I'll probably say, this might be hard to explain. It's a type unit range. You notice that it isn't a vector. So this is a little bit subtle. Hopefully you notice it. But like when you're setting up this 1 to 10, you're not making a vector. If you want to make a vector, you do something like collect 1 to 10. And that will make a vector. So when you see, like, when you're doing these for loops, you go for I in, I should just type it rather than wave my hands in the air. 1 to 10, that 1 to 10 is not making a vector and then you're not pulling elements out of it. You're making an iterator that will give you the value every time you ask for a new one. Subtle difference, but it makes a big difference in memory use. So there's this thing you can do called splatting, which will take that iterator and them out, like splat them out. That's what this thing is doing. So basically, instead of going 1, 2, 3, you can go 1, 2, 3, ... and it will splat them out and make a new argument for each one. That's a really useful shorthand. Yep.
So is it essentially like turning the iterator, like if you have a vector U, instead of writing as a vector, you kind of put them as the arguments?
You can put them in as arguments. You can use it in a variety of ways. This is one of the ways. When you're taking arguments, instead of having to write them all out, you can just splat them out. They'll go. I'll show you some other stuff later where I'll use this again, but this is kind of weird. So this is actually a way of doing factorial, a really bizarre way of doing factorial. If you want to do factorial 10, you can do it this way. If you want to do something kind of a bit more functional, there's this accumulate. Again, because I don't know what, I can't type and I'm pretty silly. If I just press ACC tab, it'll have a guess at what else is there for me. So I can go, what's this function argument? Again, if you want to know what it is. So accumulate via a function, 1 to 10. So that will make a vector. Each one is like the element in this series of going like 1 times 2 times 3 times 4, all the way out to 10. And then we can go last. It's a pretty strange way of doing it, but you can do that way if you want. And this last one is an example, is you can do it in a loop. This is a kind of terrible example because there's a little sneaky global in there. This is to do with scoping. Don't do this, but it's in the notes just to make the notes work. If you've got it in a function, my factorial x. I don't know why it's called FD. That's pretty weird. What should we call it? What's a good variable name for the factorial we're going to calculate? Anyone? I'm terrible at naming things. Anyone? You look like you're good at naming things.
Output.
Output. Cool. Okay. Output equals 1 for I in 1 to x. FD, output, times equals I. And return output. And moment of truth. If this doesn't work, no, I can't type. My factorial Factorial. Okay, hey, it worked. It's distressing that it worked.
Is there a fold instead of
Sorry?
can we fold?
Yeah, you totally can. You can do the more functional stuff. There'll be like, you can do a fold left and a fold right. I'll leave that for you because you know what fold is. You can go and have a look later. But that's you definitely can. There's more functional constructs if you want. There's reduce as well. You can do all that stuff if you want. Cool. That's a bit more functional style stuff. Cool. Okay, back to the notes. So everyone happy with all that stuff? No? Question? Oh, there's a question on chat. Great. Can you semi-apply functions like no. I think I'll take that question, have a think about the best way to answer it. No in the first instance, because it will take, like, if you just do that, it won't do anything. So yeah, I'd say to Anton, I'm not sure I quite understand what the setup you want is, but there's probably a way of doing it. It's probably a little bit wonky. Yeah, I'll have a think. If maybe in the break, I'll have a think and see if I can answer your question a bit better there. Okay, cool. So back to the definition. Again, we can make a recursive definition of this where you can go like, if n equals 1, or if n equals 0, it's 1. Otherwise, it's n times n minus 1 factorial. And you notice that definition of factorial is nested in itself there. So we've got a recursive definition of factorial. Cool. That's recursive. So you can actually do that. That's fine. So what it requires is calling the function itself. So, oh, there's one here. Someone's already done it. Okay. So this is our iterative version of my factorial. I'll just copy that and I'll talk through it because that's easier for now. Okay, my factorial. So we'll just step through this. So we've got an expression here, if else. If n equals 0, just implementing that definition, return 1. And this little bit that, like, if you haven't done much programming before, this can seem a little bit wonky that you can actually do this, but inside it, we're going, first point is you can have multiple return statements. You don't have to return one thing. You can return all sorts of different stuff depending on your function. It can be nasty to do that, to reason about. Like if you get a bit of code and it's like, it could return this and it could return that and it could return this other thing and I don't really know what's going to come out of it when I'm using it. That's generally not great, but it's sometimes necessary to do that. Yeah, but anyway, that's the first thing. So we can have multiple return values. You can return in different spots. That can be really useful if you don't want to follow on a bit of logic. You just go, in this case, just return something and then bugger off the function and then the rest of the function continues on below. So this one is if n equals 0, return 1. And then this other one, we're going to return n times my factorial called with n minus 1. So that's this function itself. My factorial, again, 10, with the recursive definition, gives the right answer. That's cool. Okay. Cool, we've got another one here. Again, I'm just going to copy this, paste it in. We'll talk through any weird syntax that comes in. Someone even asked this on EdStem of like, what's the difference between println and print? I can actually show it here if you want to see what the difference is. We'll go through this, but println just puts a new line on the end of a print statement. So it'll put a carriage return. Next bit of text will return when it goes to display it will show like it'll go down to the next line. So in this one, we're going my factorial. It's going to tell you what it's calling. It's calling my factorial blah. This is basically exactly the same with a bit of print debugging in here. This is super useful. Print debugging is a terrible thing everyone does when you've got a function and you're going, I've seen some examples of questions asked like this, especially when you got it in a loop or something and you don't know exactly the state of what you're calling the function with. It can be really useful to write that stuff out to give yourself a hint about what's going wrong. Long history of terrible debugging is like just put prints all through your code and work out what's going on. But there's better ways to do it. But that's a dirty trick that's useful. So hopefully that's clear. So it's going to say, so remember in the first one I was writing is like the last line is the return as a default in Julia. So the thing at the end is the thing it's going to return. So we can call this guy my factorial 10. Okay, so you can see it goes that if the progress of this code, we're going to, if we watch it from, so if we call it with n equals 0, it's just going to go, it's just going to return straight away, hopefully. So it's going to go calling my factorial naught, returning from the call of my factorial naught with 1. It basically just hit this if statement, return this value. If we do it with 1, it goes down. So it's sort of descending down into the function by calling itself, returning. That's basically what the thing of this one is. So you can see how it's going. Again, just to make that super clear about what the difference between println and print is, if I don't put the ln there, it'll look like a mess, but it all goes in one line. You don't get these carriage returns to return it to the new line. For that person who asked that one, it's pretty straightforward. If you want to make it look prettier, this is some stuff you can do. At info is probably, if you're writing real code, you probably do something more like this. This is a type of logging you can do. Oh, sorry. That looks a bit prettier. It comes up with this nice syntax thing. You can also do like, there's levels for that. You can also do at warn, at error. A little bit prettier. Okay. So cool, that's what it's doing. And then I don't think there's much else to show. Hopefully that's clear. This is just a recursive definition. You can see what it's doing, blah, blah, blah. Okay. Okay, we can write it super compactly. So I've shown this syntax before where you can do this as a one-liner, where you can go like, I'm going to define my factorial of n equals n. And then there's this funny thing called a ternary. Have I said a ternary before? Is this an expression? Ternary? It's like, this is a silly example, but I have seen someone use the knowledge of what the hell a ternary even is as an interview question for when someone was getting a job. This is like, you're not a real programmer if you don't know what a ternary is. So good to remember this one because it might come up again. A ternary is a weird thing. What it is we're doing, there's a first part of this. So it's called a ternary because it has 3 parts. First part is a predicate. If I say a predicate, anyone's eyes glaze over? Anyone know what it means? Who doesn't know what it means? Anyone want to say what a ternary is? Anyone who's confident? It's a predicate, sorry, predicate.
It's a logical condition that evaluates the true or false.
Yeah, so it's like a function that returns true or false. If I say a predicate, like, am I doing a lecture now? True. Or is Paul doing a lecture now? True. So that's the first bit. The first bit will be a predicate, and then you put a question mark. And if it's true, you give the first return. And if it's false, you do the second statement. So that's why it's a ternary, because it has 3 arguments. The first argument is function. Second is, what do you do if it evaluates true? And the third one is, what do you do if it evaluates false? Is that clear? Useful thing to know, because it's like you always end up writing these dicky little things where it's like, if blah, do this, else do this. It's like, comes up all the time. It's really long-winded. Sometimes it's really simple just to write a ternary instead. Cool. So I didn't say what it was. So my factorial of n equals blah. If I call my factorial with 10, hey, get the same answer. Okay, so it's even stranger than that. I think this bit's kind of cool. What we've got here is we've got these 2 definitions. We've got, as a one-liner, the recursive definition of my factorial. And as a multi-line expression that we did originally, we've got like this long-winded version where you go like, if n equals 0, which is this first part of the ternary, return 1. return 1, else return n times my factorial n minus 1. So we've got it, hopefully you notice here, it's my factorial 1 and my factorial 2. It's not a nice way in Julia. In most programming languages, you have a case statement. That's like if you've got like 20 things and you want to go bleh, but no, unfortunately, no. I don't think. There's probably a package that does it nicely for you, but I don't actually know what it is. Not in the base language, as far as I know. Yeah, so we've got here this ternary versus this one. Okay, so we've got my factorial 1 and my factorial 2. Last time we talked about some of these low-level macros. I can't remember which one I showed you. We showed code LLVM, code native. Here's another one that's code lowered. So this is like, I'll try and make sure I get this right. It's people who know me, if they watch this, they're going to be screaming at me they got it wrong. It's basically the way the Julia compiler works. So a compiler takes code, it turns it into a lower level representation that can be run on the computer. Last time, I think, or the time before, I talked about LLVM was what it is right down the bottom, low-level virtual machine. That will get converted by LLVM to native code that depends on the CPU you're running. Before that, though, there's this intermediate representation where you're going like from Julia syntax to something that can be passed to LLVM, and that's this code lowered. So this is another way of interrogating like what this syntax, this stuff I'm writing out on my screen that's sort of human and nice, what that gets turned into in this descent into hell before it ends up on the CPU and it's doing all these weird logical operations that are hard to follow. You can look at this with code lowered. We'll look at my factorial 1 with 10. Okay, and code lowered my factorial 2 with 10. Hey, look at this. So we have these two different definitions. One's based on the ternary, one's this long-winded expression. They both evaluate to the same low-level code. So it doesn't care, it's just for you. So in terms of comprehensibility, like which one's easier to follow, it's like sometimes it's nice to not have a disgusting amount of code, having it nice and short, but also there's a mental overhead, and like particularly for people who are new to the language about, do I understand what this is doing? No, well, if it's the lowered code is like it'll get parsed. So there's a parser that will run over this code, turn it into the lowered representation. That might be faster or slower, but that is a tiny, tiny amount of runtime. In terms of execution, they're both turning into the same machine code in the end, because the lowered representation is the same, the LLVM representation will be the same, the native representation will be the same.
In Julia, when it's running the code, does it read it? Like, is it like a script, or does it turn it into this code?
It's just in time compiled. So like as it runs, complicated story. Andy will talk a lot about this. I'll just say a little bit. It's like, it's just in time compiled to this native representation. So like when you go to run the code, it will go that way. It's not like you have to run a compiler, like if it was C++ and it runs the compiler runs for ages and then you've got a fast executable. It will do this just-in-time compilation. So when you go to run it, it'll work out the types of everything, work out a fast implementation and go from there. It's kind of, it's good. It's like the technical achievement of Julia is having a language with multiple dispatch that's just-in-time compiled that's actually still fast. That's like a thing that's not happened before Julia. Probably happened with lots of other languages post, but it's kind of, that's one of the things. Because it's nice to have, I won't talk about this too much now, but different styles of programming languages, like let's say like dynamic versus static, maybe that's a bad way, but these dynamic languages like Python, Julia's kind of dynamic in a way, but it's faster to develop in typically. So for a person writing code, it tends to be quicker. If you've got a statically or strongly typed thing where you've got to make sure the type of it, the type of everything all the way through the code, like C code, and you can't do any of these funky work it out later types of things. It tends to be more overhead for the developer because you've got to make sure everything's right. But you also it's easier to catch bugs, so it's kind of a trade-off. Anyway. So that's kind of cool that this lowered representation in both cases is exactly the same. Cool. All right. Did we talk about big ints? No, I didn't talk about that yet. Okay. So the question I'm going to ask is like, who's read the notes first? Like, does anyone know what the answer is going to be before I ask it ahead of time? If you haven't read the notes, who wants to have a guess about how big a factorial can you take before int64 is not enough? So if we were talking about uints, you know, what's the biggest uint? It will be like, if it's a 32-bit uint, it'd be like 2 to the 32. So 4 billion-ish, I hope, if I can count. And 64, 2 to the 64. That's not going to work. That's not going to work. I have to do it as uints. Anyway, let's do the real thing. Type max. This is a useful function. Have I shown this one before? Type max. Does that come up in the note? Yeah. Type max is really useful. So if I go int64, because remember we've got this 2's complement representation where there's like they're sort of counting up from the bottom and then they click over at the front and count up again. That's a huge number. I can't even count how many zeros there are there. Whatever. Yeah. Let's see if we can trick it to turning it into a float. Then I don't have to count. 10 to the 18 out the back. So big number. So type max of int64 is a pretty big number. Type max of uint64 is an even bigger number that's going to come out as a hexadecimal because you want to know that you're actually dealing with a uint or a thing. But you know, you've got twice as much because you don't have to worry about the negatives. So that's a really big number. What sort of factorial before we blow over that? Anyone want to take a guess? Yeah, 100. Anyone else? Yeah, that's pretty much bang on. 20 is the answer. So like it blows up really quickly. So this thing's growing. It's like every time it goes up really quickly. So you don't actually get many. You can't take a factorial of a big number without this thing exploding. So the question is, how do you actually like, say you're doing, who's doing physics in here? Lots of people. Anyone doing statistics or combinatorics? Not less, but you're still cool. You know, you might want to do the factorial of a big number, like comes up all the time. So like if you're, say it's like a probability thing where you're going to go like, I want to divide, you know, how many ways can this thing happen under this many combinations? You get these things that involve a factorial all the time. So how the hell do you take a factorial, like practically when it's like more than 20 things? That's the question, right? Like it seems trivial. Like you should be able to just go, oh yeah, factorial 740 or factorial Avogadro's number for someone doing stat mech. And you go like, yeah, of course you can take that. That's fine. How do you do it on a computer? That's what we're going to try and sneak up on here. So to that point, has anyone who's done stat mech or combinatorics or statistics, do they know of Stirling's approximation? Is that something that's come up before? Raise your hands if you've seen it. Yeah, cool. Not many other people, but Stirling's approximation is a very weird thing because I'm going to get this wrong, but I'll just say it anyway because it's fine. The way you derive this is you truncate a divergent series. Is the normal, I think it's the historical way they derive this equation. So you do an approximation to n factorial. That's actually a divergent series when you do it, and then you truncate it a couple of terms, and that ends up being Stirling's approximation. So even though the full expansion is divergent, the truncated one is fine. That's super weird. Anyway, that's Stirling's approximation. So clever people, you know, before computers were even a deal, like, you know, we're saying about someone trying to add it up on a slide rule. How the hell do they even do that? Some clever person's come up with a functional approximation to n factorial, and this thing's called Stirling's approximation. Yeah, you can go read through Wikipedia about how to derive it, but has an interesting history. And it's like, it pops up all the time in stat mech. That's where I remember it from in my undergrad, like comes up there. There's a bit of a thing here about why this is a reasonable approximation. Basically, it's decomposing this into parts. So there's going to be like this n to the n. So first question is, why is n factorial less than n to the power of n? Because it's always one less every time. If you look at the recursive definition of n to the n, like It's always going to be less. And there's basically some correction factors. I'm not going to go on about that bit of the code too much here. This is just, I think it's less interesting. Interesting bit of syntax here. So I'm tempted to do that bit, but okay, I will do that. I will do that bit. In here, again, can anyone remember what this type of expression was called? Sorry? I mean, more the, no, there's more stuff going on here than probably what you can see. If I just have this guy, list comprehension, so that's what the first bit of this code is. The second bit is putting it into a special data type, which syntax you wouldn't have seen before. So that's probably why it looks a bit like a ternary, because there's like 3 things going on there. This is called a named tuple. So that's what you're saying. It's a 10-element vector named tuple, and there's these names. Basically, the syntax for a named tuple is you can go like, hello, oh, whatever you want to call this thing. So blah, blah, blah equals 3. That looks too much like the last one. Equals. So that's a named tuple. And you can get the values back out of that later on, but don't worry about that. That's a little bit of syntax. Come back later on. I'm going to talk about in section 2, I'm going to talk about dictionaries. So this will come back again. But basically that's all this guy is. I just point out the syntax less than the thing. And this is basically looking at the factorial ratio between the factorial and n to the n, and shows that as you get bigger and bigger, you know, the difference between factorial n and n to the n gets really small. That's all that bit is. And this is a bit about how, again, if you wanted to look at like something like the relative error in Stirling's approximation, we've got an inline definition of Stirling's approximation here. That'll be useful to run. That'll be interesting to run. So Stirling 10 factorial 10. So Stirling 10 minus factorial 10. It's, you know, that's pretty, 30,000 is pretty big, but as a relative error instead of an absolute error, it's probably okay. Yeah, it's not very big compared to the size of factorial. And it gets smaller and smaller as you go up. That's basically all that stuff is going there. Basically, the whole point of that is we can use Stirling's approximation to validate your extraordinary guess of 20. So it's perfect. Basically, we're going to go, if it's uints, we get 2 to the 6, or uint 64, we get 2 to the 64 minus 1 is the max value. Max, sorry, I'll just do it again. That's that guy. Signed integer by default. Yeah, so just notice that bit, like if you actually, this was the calculation I was mucking around doing before. If you do that, because of this overflow stuff, you're going to get something silly. So you can't even, as I said, like if you just type an integer in, what's the type of that going to be? In 64. So it's not big enough to say what the biggest u in 64 is. That's what's going on there, because it's too big. It goes out past the end. So there's a tricky way of doing that, of saying it, doing the calculation in uints. But anyway, it's a big number. Yeah, so floating point, I haven't talked about floating point, exactly how it works. Type max of float 64. Oh, that's not helpful, is it? How did we do it here? Yeah, oh, it's inf, but anyway, it's not that big. Because you got 3 special values in floating point. You've got inf, minus inf, and nan. They're kind of like the not finite values of floating point. So if you say, what's the biggest floating point? I say infinity, but it's like, it's not really infinity. We'll come back to that later. But anyway, so this is basically solving for that by brute force. There's lots of ways you could solve this. Leave it as exercise for you guys to come up with different ways of solving this, of how you would solve for n. This one is the easy one. You just go like, for what value of n does the Stirling's approximation blow past the limit? And running that, you find out it's 20. So there's also an easier way to do this. So hopefully the person who wrote the code knew what they were doing, and they go like, yeah, cool, I can do factorial 20. If I do factorial 21, it doesn't eat my computer and everything explode. It just comes up with an error going like, oh, that's bigger than I can know how to deal with. So this is really funny though. Anyone notice anything here? Because there's only 20, someone's just done that thing you're asking about. Can you have a case statement? They've just written a table and gone like, I'll just look that up because it's quicker than doing calculations. So there's a table somewhere in Julia that goes like, if you call factorial with a uint or an int, just go look it up in this table over there and you're good. It's not even doing anything. It's just like looking something up. But that makes sense, right? Like this thing about computational complexity, like, does it make sense to do these implementations we were talking about where it's this recursive definition or this iterative definition when there's only 20 ones that make sense? No, just do something else. Cool. Now we can, this special thing though is big. Oh, that's special. It actually did something. Does anyone want to guess what big is doing? Yeah, that's right. So like 64 bits is special because we use 64-bit CPUs, right? That's why it's all, I don't know if I said that, but that's like, I probably should have said that in the first lecture. Like 64 is special because the computers we use now, back when I was younger, 32 bits, if you're on an Arduino or something like that, 16 bits is what you get, is the natural thing. You can always burn 2 cycles and make a bigger thing in memory. That's one way of doing it. But basically, if you put it in memory, like you're saying, you can have virtually unlimited size. So there's no, everything's just going to be slower. So these things I was saying of like, how do we do addition with uints? This is why I was doing it in the first lecture, is there's a special thing we can do on the computer with logic. Once we go to big ints, we have to implement all that stuff ourselves. So it's a bit slower. You wouldn't do it with logic, you do it another way, but this is the thing, you can change the type to get more flexibility, but you have to implement more stuff for that type. So if I go big 21, doesn't give you much of a hint about how it's displaying. It's a big int. And if you want to hint about a big int, again, just go to the help. Arbitrary precision integer type. So it's arbitrary to the limit of your memory, right? Like if you could, you've got a finite amount of memory on this computer. I think it's 16 gigabytes of memory. You start trying to make a big int that's too big. That'll be not enough, but then you can go use the file system. You can start writing stuff to your hard drive. There's probably a couple of 100 gigabytes there. So practically unlimited. This will come up when you guys are doing Paul Verbeek's section, because like when you're doing, shouldn't put my hand over this thing. When you're doing this polynomial stuff, like the computer algebra section, the integers can get really, really big, really, really quickly. So you need to be able to deal with that. So having these arbitrary precision integers is a cool thing. Yeah, so you can do, yeah, you know, we couldn't do 20, but now we can do big 10 to the, oh, type of, that's not helpful. I wanted factorial. Oh, too big. I went too big. I got excited. Anyway, so yeah, that's the story of my life. 10 to the 3 you can do, apparently you can't do 10 to the 75. But that's, maybe that's probably limited my memory on my computer. But in principle, arbitrary precision. In practice, not so much. Okay. Any questions on that? Big ints are useful type, you know? Not everything's uints and ints. If you're having problems because of, you know you're going to hit overflow, there are these other types to help you out. That's the point of seeing that guy now. Any questions up to now? Happy? Okay, good. Okay, next bit is Okay, what happens if we try and do it for an arbitrary real number? As a mathematician is wont to do, you're going to go like, hey, I defined this thing that makes sense for integers. How do I make it make sense for other things? So like a factorial of a real number. It's like, nah, cool, don't get that. Haven't implemented that. There is in mathematics, it's not my generation, but the generation before me. They didn't do a course like this. What they would have done a course on was a course on special functions. Has anyone ever heard of those before? It's kind of a wonky thing when more stuff was analytic in maths. So the one I always have, because it was in my honours thesis all those years ago, was Bessel functions. Has anyone heard of a Bessel function? When you have cylindrical symmetry and you solve certain types of partial differential equations and that, the natural basis function of these things called Bessel functions. They would have done a course, like my lecturers would have done a course on special functions instead of doing a course on numerics, because there's a whole bunch of these things you had to learn. Now nobody knows them all. One of them is a gamma function. Has anyone heard of that guy? You've heard of a gamma function. What context? What's that?
Yeah,
factorials. Okay. Yeah, cool. Comes up in physics a bit. Oh, I don't have gamma. So what I need to do, using special functions, gamma 0.5 or 6.5 in the notes. That makes sense. Okay, so there's this thing that can define gamma function. I'm going to talk a little bit about this. Just want to check. Yeah, I'll talk a little bit about this just up to the break. I noticed you're probably all getting really tired. Okay, so the way the gamma function is defined is this funny integral definition. So it's like it's a definite integral between 0 and infinity of x to the z minus 1 e to the x dx. That's the value for z. So you solve this integral. You need to solve this integral for each z you care to evaluate. Okay, this might seem a bit of a discursion, but what we're going to do, I kind of want to introduce this, and I'm going to talk about it again in unit 3, is like, we've got an integral here. What's a plausible mechanism for solving an integral on a computer numerically? Anyone want to have a guess? What's the way? How do you learn what an integral is when you're like in, I don't know, is it high school or first year uni? Like, yep. Yep. So the fundamental, like, I don't know, some of you guys are going to have done more analysis than I ever have. When you first learn calculus, right, you go like this idea of a Riemann sum, Riemann integration. So I drew a little picture just so we could see it. So I've got some function f of x. A way to approximate this integral for a finite step is you chop the domain up into regions and then you put a polygon in there. And the idea is that I know somehow what the answer for the integral of this little polygon is, and I just sum them all together. So it's really easy to work out the area, integral's the area under a curve. It's really easy to work out the integral for a box, it's just width times height. So if we're going to do lots of little boxes and then shrink them down to find tiny width, I take the limit as it goes to 0. That's a good approximation for the integral. So a really nice thing with maths applied to programming is a lot of these ways you would define it actually generate an algorithm for doing it too. It's like if you go, okay, I'm just going to chop the domain up into little boxes and sum them up. That's an approximation for the integral. As I make the boxes really, really small, it gets a better and better approximation. So someone said about trapezoids, right? You said trapezoids? That's like the first order way you could fix this. Everyone can look at this and go like, this is crap because this is flat. I could probably do a better job if I just like cut the top off. And that's a thing I can possibly work out the area of too. That's like the next best approximation would be to do that. Anyone want to guess what the next best approximation might be? Yep, the quadratic. So in general, a spline, like you go like, I'm going to do some interpolating polynomial between the points, and then, I can work out what that integral is analytically, sum all those guys up together, and done. Good answer. That's kind of what we're doing here. what this guy is this is the, I want to say the integrand, the bit under the integral. That's just that guy there. And we're gridding up the domain from 0 to m. So m is hopefully a big number because this is infinity. So, you know, is 50 a good approximation for infinity? Depends on the problem. Sometimes it is, sometimes it's not. So in this case, it says crude, so we're fine. So like we're just going to go from 0 with some discretization delta out to m. So basically we're making those boxes. We're going to evaluate the function and multiply it by that. And we're just going to sum it all together. And that guy is where I will run, and then I'll take a break for a second. My crude gamma 6.5. So yeah, cool. We run that minus gamma 6.5, the built-in one by people who don't think 50 is infinity. You know, so they probably know what they're doing. Oh, that's tiny. That's a tiny, tiny difference. Like, so that's probably fine. So like with Riemann integration, you know, we've got reasonably big steps. Again, if I want to change the basis, so let's see how bad it goes if I make the basis a little bit bigger. So instead of being 0.1, I'm going to make my boxes 0.5. That error gets worse. It's terrible. It's really bad. That's how you would interact with this function. Sorry, the point of doing that is just to show, you know, if I make this bigger, it'll probably slow down a lot. That m, so you can sort of do a numerical experiment and show that, you know, 50 is a good enough approximation for infinity for this problem because it's not contributing to the integral very much. Okay. That's how you do it. So Riemann integration as a mathematical definition for how you do an integral turns into a nice little algorithm that you can run and gives you a hint about how to solve real problems. That's the point of doing that one. You've been introduced to a new type, a big int, in case you're going to run out of precision. Lets you do arbitrary precision apart from 10 to the 75, 10 to the 3, you're okay. Okay, cool. I'll take a break for 10 minutes now and we'll come back. Okay, I'll get started again if everyone's happy. Yep, cool. Good catch. Evaluating the code. I really like people evaluating the code as we go. My crude gamma dies if you try a number less than 1. It comes out with an inf. So I'll leave it as an exercise to everyone else to work out what might be going on with that one. It's an interesting one. If I can tell you what there is at the end, if you want to have a look. Anyway, that's cool. It's easy to fix, thankfully, but it's like a nice example of a real problem. Yeah, so good catch in the notes. Looks like a typo here that looks similar to the definition of factorial. The recursive definition of factorial is that the reason it's called the reason you can think of it as the continuous version, the version extended to the reals of the factorial is that it superficially looks similar. If you crank through the notes, you can see that there's this recursive definition for the gamma function as well. Yeah, so an interesting thing is the gamma function itself is defined for negative integers, but some of them gives you a domain error. This is to do with the math stuff. This is like a maths bug. It doesn't work at some points in the real domain. It's peppered through with spots where it won't work. This is like what do I want to do? We will show a plot of, this is just some syntax for plotting. This will be useful to see. Hopefully my plotting works. You can generate this plot. For your homework, you're going to be doing lots and lots of plots. You'll end up getting better with plots than I am. I don't really use it that much. So the named arguments for this one, it's kind of like a hangover from matplotlib. Like I think underneath plots is just a front end for lots and lots of backends, we would say in software. So it's like plots isn't making the plots. Plots is wrangling your stuff and passing it off to other programs to do the plotting for you. And one of the backends for plots is pyplot, which is calling matplotlib in Python if you've used that. So basically, you can figure out, if you're familiar with matplotlib, you can figure out the API, application programmer interface, of like how you'd call this thing and give it. The documentation for plots sucks. I'll give you that. It's kind of terrible. There's another one called Makey that people I work with who do more plotting than I do use that more often. It's much prettier and nicer. So have a go at making, you can make some really cool plots with that. I'd recommend going to, maybe we can do it now, but going to the demos in, they're better than anything I'll ever make with this thing. I'll end up making crappy plots. You can make some cool visualizations with this one. So like a Lorentz attractor, really big in the 90s. Some examples here that look really cool. Where are we going? We'll go for examples, plotting functions. There's some image stuff and ray tracing stuff. Yeah, to the limit of whatever you can deal with, this will be better than that. So recommend having a look at that one. Don't just get stuck on using plots. I just use plots when I'm hacking stuff out though. But anyway, I don't know what my point is there. But basically, this is a plot where it will give you a rough idea of where these singular points are. This thing's going funny at 0, and it looks like it's funny on the integers. Like it looks like it's got this swooping up and down to infinity at the integers. Question for people who are excited about maths to go off and show me why it's undefined for particular values. I don't actually know. Okay, cool. So, I mean, this is kind of an interesting thing, I think. Interesting bit of time we're at the moment where like natural language processing has gotten good. Like my career, said a little bit about what I've done in the past, but like I can remember you go through these periods of people get really excited about something in software and then they go, oh no, it doesn't work as well as I'd like, and it drops off. And one of those was neural networks. It's like when I was an undergrad, neural networks were kind of like in the bin. Like people didn't really use them for anything. There was some good successes with like digit recognition for putting letters in the mail. I think that's Jan LeCun was doing that one in the 90s. So like you can recognize that it's a 6 or a 0 on the postcode. So they put all the letters through that. That was actually automated in the 90s, which is kind of impressive with neural networks. But everyone like got really excited and then they got really not excited in the 90s pretty much. So in 2000, it's like, yeah, cool, natural language, neural networks, nobody cares. In my career, working in remote sensing, so that's like looking at stuff on the ground from a plane, basically, or a satellite. I spent a good 7 years working in that area. Around 2012, it's like everyone got really, really excited about neural networks because they started working for images. It's like before that, there's all these special hard-coded things to do image recognition and all these funny things that don't make much sense. And then suddenly neural networks started really, really, really working, and they started beating everything else by a long margin, which is really interesting to have worked through that. So I was in that. It's kind of really interesting to have gone through that and seen it. And then it's kind of like, cool, that works really well for a fixed size array when you get text. And like text is this funny thing because it's like, you can always put another character in and it still makes sense as a sentence, right? It's like not like an image where it's always this big by this wide, you know, this long by this wide. And it's a nice regular grid. In language, it's like you can say a sentence and the point of the sentence only becomes apparent right at the very end of the sentence, what you were talking about at the beginning. So there's these really long range correlations in the thing. And it's like you guys are actually in a super exciting thing now of like natural language got really good in the last year or so, and you probably noticed, right? Like the GPT is in particular is the one that everyone is excited about, general purpose transformer. I'm not going to teach you how to do that because I would be underqualified, but it's super interesting. Like you're in a good point in time because it's really interesting to see this stuff come through and learn about it. Anyway, so the low level bit of that is like, how do computers deal with text? Fundamental type, we talked about this last time. We go like, my name equals Janet. You've got this funny size of function. It lies to you though. We'll come back to that later. For anything more complicated, so it's the highlight here is the canonical binary representation of a given data type. See, if you have a complicated object, yeah, it'll lie to you about how big it is in memory. So I'll show you a trick for getting that one later on, but not at the moment. So we can do size of Janet, size of my name. You know, string manipulation is one of these things you're going to have to do. So size in bytes of this thing, because it's 5 long, you're going to get 5. It's 14 long. Cool. This is an array pretty much underneath. So you can use the array indexing things to get the elements out. If I go my name 1, again, going to make some people mad. First thing in the array and you'll hear is a 1, not a 0. If you do 0, you're going to get balked. It's going to go bounds error. You can't do that. Don't do that. You can do this, or you can do begin, which is a better way to do it. It's not actually a true story that it's zero-based indexing. It's actually, if you want, it's arbitrary indexing in Julia to make it really exciting. So you can start from -257 if you want to. There's a package called offset arrays that lets you do that. And one way you can get bugs in Julia between packages is using things like this 1 to the start of an iterator. You can go like, oh, I want the first one, so I'll put a 1 there. Then another package using your package will go like, I'll pass in a weird thing that doesn't actually start at 1, and you'll get the wrong element of the array. So use begin. Or in is the other one. So like sometimes when we're writing these for loops, you'll see me like go for I in X. Better way to do it because it always starts from the first and ends at the last, rather than going like for I in 1 to length of X, X, I. That's a bad pattern. Don't do that. Don't do that. I'll do it, but don't do it. Anyway, what was I talking about? Here, begin. You'll see the type of that is different than the type of the string. This is like what the little bits of the string are made up for. String is just like a bunch of characters stuck together. I don't know why it's called a string. Does anyone know why it's called a string? I've never actually had that explained to me. I don't know why, but it's basically just a bunch of characters stuck together. The first one is this special character type. Says a little bit more about it. Type of is type char. So like if you want to make a char, you don't actually use the same thing. I can't remember which ones you use. It's like those. That. So it's like single quotes for a char, double quotes for a string. That's what that goes. Okay. Cool. Yeah, I don't know why. This one, yeah. So concatenating strings. Concatenation, if I say that, that's a bit of a software wonky word that if you're not doing it, concatenation just means sticking it together. The way you would concatenate two strings is you can go like A equals we and B equals. If I want to stick A and B together to make one string out of the two strings, you just go A times B. Okay, that's all. So you can, that's the operator for strings. So you get this idea, I'm going to say this because it comes up in Julia, dispatch on types. So the function depends on the types of its inputs. So if I call times with two ints, it will call this method that will do multiplication of integers. If I do call times with two strings, it will do concatenation. That's one of these things about Julia. So like the type of what you get from the function depends on what you put into it. That will get more important later, but I'll just keep saying it as we go through. But that's basically, so if you do something like, you know, if I want to put a space between A and B, I can just go make a string with a space in it, and then I'll get squee pluggy with a space as two words. Cool. Yeah, that's kind of wonky. You can do this if you want, if you want to make Janet, 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 with spaces. So begin to end -1. Okay. Okay, this encoding is called ASCII. Again, it's like we were talking about, how do you represent an integer in bits? Cool, we've come up with two ways of doing that. For an unsigned int, it's 2 complement. Oh, sorry, no, it's just the straight, whatever it would be in. Say that back to front of what I actually meant. If you're doing a signed integer, you do the 2's complement representation to do bits, and if unsigned int, you do the opposite, do the obvious thing of just going like, you know, powers of 2. ASCII is what people have decided on for characters. So this is a standard character encoding. Yeah, cool. That's pretty much it. It's like, I don't know when it was, dates from. Bell Labs, pretty famous. Probably the telephone company in America did a lot of stuff to do with software and a lot of stuff to do with physics, and kind of crazy place. It's become a standard eventually, so that's good. But that's pretty much ASCII. For some reason, the first 32 are white space characters, so they're nothing, just sort of like, they won't give you anything. So this is a little bit of code that will write out a rough ASCII table. It will go from in hex. So what's this guy as an integer? Can anyone do that in their head? Anyone want to guess? I think I just said what the answer was. Like the first one's a white space character, so we don't want to show those. So that's 32, yeah. So it counts in 16. So 2 times 16 is 32. Okay, so that's that. And yeah, I'm not even going to try with that one. 7E. Yeah, 126. So we're going to just show, just make a little table, iterating through, showing all the ASCII characters. So this /t is for a tab. When you're doing print statements, if you want to put a tab, usually 4 spaces in between characters, you do the /t. If you want to do a new line, /n, that was the println versus print. It's going to turn, so C in this, we're going to turn it into a string base 16, and we're going to do the char of this integer representation. So this integer has a char, and this integer, we're just going to turn it into the hex value of it. So that will see all these characters that you might use as, you know, for writing most simple things are one of these ASCII values. And they've got, each got a, how they're stored in memory, you can interpret as an integer. Make sense? It's pretty arbitrary, right? Like this is like, the integer one is less arbitrary because we want to do like things like addition. This one is completely arbitrary. Like there's no special order to the characters. Like we do it for memory, you know, A, B, C, D, E, F, G. If you think about types of measurement and stuff like this, like is A closer to B than A is closer to Z in any sensible definition of closeness? Does that make sense? Like they're not really ordered in that way. They're only ordered in that way for our memory, for purpose of memorizing these things. So characters are kind of arbitrary. So you need to come up with a standard. And ASCII is one of these standards. Okay. So one of the things you'll notice though, is they put all the uppercase characters starting from hex 41. They go up to Z, and then there's a bunch of stuff in between, and then with an offset, then you get all the lowest case characters in order. So maybe this is a homework question or not, but you'd be able to see that like from first principles, if you wanted to go make an uppercase function or lowercase function, you might be able to see how to do that. Anyone got any ideas about how that might work? Yeah, that's right. So if you're going to lowercase, you would add an offset to the int representation of that char. And if you're going to uppercase, you would subtract off the offset for the int representation of that char. Make sense? Do you want me to? Everyone happy? Yeah, cool. No one complained. That's good. Hard to get excited about this stuff, but it's important. Okay. So this one. So this is important. Just make sure you got it in your head what this means. Okay, this is testing for equality. So like programming languages, it's kind of weird, I guess. Equals is assignment usually, and equals is testing for equality. So this is like another predicate thing. You go like, I'm going to go equals, and this is one of these special ones where you've got an infix representation where you can put the arguments either side of the function, or you can do equals brackets. So you're allowed to do 1 equals 1. True. Not so interesting if you're typing in the actual values, more interesting if you're actually evaluating a function. I was going to go something like x equals 5 for x in 1 to 10. This is going to make test for equality as I go through this iterator. And somewhere in the middle it'll go, yeah, that's 5. That's the more like how you would use these things. But anyway, that's the point. So that's what those things do. So if I make the char for A and I make the string for A, anyone going to make a prediction of what's going to happen? Are they the same thing or are they different things? Different. Yep, that's right. But if I take off the first element, no, they're not actually equal. Sorry. That's false. That's interesting. Why? Oh, capital. Yeah, good. I was having a little moment of existential crisis that the whole world's fallen down. Okay, cool. That's good. It's slightly embarrassing, but that's good. Yeah, so everything makes sense. So the char, if you suck out that thing from that array and you test that it's the same, yeah, I guess this one's less compelling as a demonstration, right? It's still false. Yeah, cool. So the char, again, char and ASCII value are different. It's like the container versus the element in the container. That's the way to map it in your heads. And again, this, I'm pretty sure it might be a homework thing. If like the difference between these two, you can do a difference because they've got an integer representation underneath. You can do the difference. They're offset by 32 from each other. So if you want to go uppercase to lowercase, you know, get the integer representation, add a bit, reinterpret it back into a char. Yeah, so it asks you tellingly how you might do that. And there's built-in functions to do this. So it's like silly to do this. I was actually using this today. I had some random stuff. So it'll go AS. So it'll turn them all into uppercase, or alternatively, you've got lowercase. This is really useful when you're trying to programmatically interrogate a text file. You know, like sometimes they'll have people, it's always the problem with people getting at files. So like if you get some data from someone, they'll have randomly changed the cases of things and you've got to try and deal with that. These functions are really useful for that parsing. Okay, this one's going to get interesting really quick. So Here's an example from this book. So this idea of a text corpus. So this guy, Shakespeare corpus. Let's go that. So what we're going to do, this is going to, again, jump to some stuff you may have heard of, and it's trivial for you, have never heard of this before. We're going to do a HTTP request to a website. We're going to get data from the internet, basically what this is. So there's this library called HTTP. You can do a type of request, and the type of request is a get. It means get data from this place. I'm going to go, please give me data at this address. And this address is the MIT OpenCourseware. I don't know what this lecture is. I don't know where it came from, but it's like so this will be a little bit slow. Hopefully this is a problem with notes online. There's every chance that this thing's dead, this link's dead, and I'm not going to get anything back. And this demo is not so good. It is good, it's still there. So here we go. So what we've got in here is a bunch of stuff. So data, blah, blah, blah. eText file of Project Gutenberg. So anyone familiar with Project Gutenberg? Heard of that? Anyone not heard of Project Gutenberg? Yeah, does anyone want to say what it is?
Like old text in the public domain.
Which is, yes, so it's super interesting for talking about these large language models. There's a lot of problems early on with them being like horrifyingly racist and things like that. And it was because what ends up in the public domain, and it's like self-published things and old things. So, you know, old man rant that's like, you know, yes, exactly right. So anyone recent who's written something is like, that's open to, like nobody else wants to publish it. I'll self-publish this thing. It goes in the public domain. It's like crazy rants about aliens and lizard creatures, and the old stuff, you know, is going to be the old stuff. So actually building up these libraries is like a big deal for anyone who does machine learning. It's like making a good data set underneath so you don't get strange things going on. It's really easy to just scrape heaps of data and get like a huge, I'll prepare for that demo. Hopefully, I hope they haven't fixed it with ChatGTP, but there's a fun demo for a blind spot for ChatGTP based on someone's Reddit username, but I might come back to that later if I prepare for it. Anyway, they'll probably have fixed it by the time I get back to it. Anyway, so Project Gutenberg, they just go like, here's all of Shakespeare. So we can go this, I hope I don't destroy this by interrogating it, but we go type of data. It's this thing, it's a HTTP message. Part of this, might need to do the request, is like this thing's got fields. Haven't talked about structs yet at all. So this is like, we've talked about types, you know, arrays, ints, whatever. More interesting is when you're going to do this composite thing. Like I'm interested in modeling a thing in the real world and I want to make it from lots of different things. When you get to Andy's bit, he'll go really deep into this. I'll just sort of vaguely introduce it. But this is a more complicated type where there's a bunch of stuff in there. So again, Julia, REPL stuff, if you go dot and then you press tab, you'll see all the secret hidden fields in this struct. You can also do the more intelligent thing. Field names, I think it is. Oh, no, I don't have that. No, that doesn't work. Anyway. Oh, well, don't worry about that. Someone hasn't implemented it. Okay, so that's got a body, it's got headers, it's got the request itself, it's got status, if we want to look in the headers. So this is all stuff to do with doing an internet request. It's going to go like, cool, how do I do it? How do I do the handshakes to make sure nothing dies? But you know, it's really crazy that you're talking to some computer here. Like how hard this used to be versus how easy it is now. It's like I'm talking to a computer on the other side of the world dynamically in a lecture. It mostly, like 99.99% of the time, it's going to work and not time out. It's crazy. And I just downloaded all of Shakespeare, like in a couple of seconds. It's kind of wild. That's to do with the headers. This will have the request itself. That's what I asked for. So I asked for a GET request at this thing, blah, 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 some extra stuff. Yeah, and versions, because there's different versions of stuff. But anyway, the basic thing I want to do is I'm going to take the body of that HTTP response and I'm going to turn it into a string. Okay, so size of Shakespeare. Oh, cool. It's not very big. Yeah, so it's not huge. It's like, you know, that's a pretty small thing. So what we're going to do a couple of things here. We're going to do a split. So Shakespeare words. What this will do is it will go through all that Shakespeare as a string and split it on the spaces. So the default split, I'll show you this. Split takes a string based on a delimiter. So the default delimiter, pretty sure it's space, but anyway, that makes sense. So but you don't have to split on that. So I can go like, for example, if I go split, splits it at the space, makes those 2 bits. You can give this, say I'm a crazy man and I want to split on Ds, I can do that too. And it'll split on all the Ds. So this is a way of dealing with stuff. You notice that when I did the second one on this here, there's actually a space in there, you know, so it's not splitting on the space anymore, it's splitting on the Ds. So what I did was just racing through it. So I'm going to split all these words. And that's like all the words of Shakespeare. So 900,000 words. It's like, this is the thing. It's like somebody's life work, 900,000 words. Suck them onto my computer over the internet. It's kind of wild. Okay, so this is another one. This is Yoni's textbook, Stats with Julia book. So basically doing the same thing as JSON encoding. We can do that. We can get somebody else's enormous amount of effort. This is a small one. Oh, no, sorry. What we're doing is we're getting a dictionary from, this is a bit more clever. I thought it was downloading a whole textbook. No, it's not. It's just getting out some common keywords. So heaven, hell, man, woman, boy, girl, king, queen, prince, love, hate, knife, English, England, God. This is a set of keywords that we got just off the internet. That was just from Yoni's book. So basically, this guy is a dictionary. I'll talk a bit more about JSON later and talk a bit more about dictionaries later too. This is probably like the first, have we seen a dictionary come up in this course yet? Probably not. Dictionary is basically what you would think it is. It's a useful data structure that has keys and values. And each key is unique. That's the thing to remember. And they're not ordered. So if you want to get something, if you want to, it's a nice little container that goes like, I want to keep things in this dictionary. If I want to get something out, this is a dictionary with 2 elements. Num to show 5, or I can get words. That's a vector of words. So this is like a useful container for a composite data type sort of thing. It's like what a dictionary is. Okay, so what we're going to do is we've got keywords and number to show are the 2 elements of that dictionary. What we're going to do is we're going to go through Shakespeare. Oh man, this is a bit of an exotic one. So what we're going to do is we're going to pass through an anonymous function, Shakespeare words, and we're going to count up how many times they occur. So I'll just do this super quick. This has got a lot of syntax we won't have seen. So as I was saying, this useful thing about lowercase is like, you know, if the turns up as the first word in a sentence, it'll have the capitalization, versus in the middle of a sentence, you know, it won't have that capitalization. Way to deal with that is to just lowercase everything and then you can do the match. What this is doing is going through, counting up the occurrences of the word knife in the works of Shakespeare, the occurrence of the word hate, God, etc. All these keywords that came from this second request. So that's a little example of coming up with basically a histogram of word frequencies within Shakespeare. Cool, so that means you could show, you know, we can also sort, which is going into the nice one, so what the most common words are in this corpus, according to this dictionary. So collect word count, blah, 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 blah. Okay. So king is the most common thing, girl is the least common thing. This seems a bit arbitrary. This is just showing some syntax. I won't talk about it too much because we'll get on to the next bit. But I talk about the genesis of these language models. Like the first useful application of machine learning to, I'd say, this text processing that most people would have noticed is spam filtering. You know, when email started, every second email was spam email. And we've got this, if you think about it as a maths problem, we want to go, or a statistics problem, we want to go, what's the probability that this email is spam or not spam? That's the kind of thing you want to do. And the ones that are highly likely to be spam, you want to filter off to the spam folder. Ones that are not spam, you want to go to the normal inbox. And you have this problem of, like I was saying, like a sentence is arbitrarily long, right? Like there's a sane upper limit to the length of a sentence, but you know, it's kind of arbitrary. Like, and an email is just, you know, you can have paragraphs, you can have this long thing, or you can have this short thing. So how would you possibly encode that into something you can come up with a statistical model for spam, not spam? And the earliest one was something a lot like this, where you completely ignore the order of words and you just do a histogram of word frequency. So you're going to go, let's collect all the emails I've ever seen, say up to some sensible limit, containing spam and not spam. We're going to go, let's make a dictionary of keywords of like the top 1,000 most common words you see in emails. And then what we're going to do is for every email we get, we're going to go count the occurrence of each of these words in this dictionary. Then you've turned this arbitrarily long thing into a finite length vector. You've just gone, how many times did I see the word king? How many times did I see the word man? How many times did I see the word love? You know, this is, if I see king, love, man, sir, God, queen, heaven, prince, woman, England, you know, it's more likely to be Shakespeare than it is to be a spam email. So this is like a encoding for Shakespeare versus not Shakespeare. You can come up with a simple histogram that ignores word frequency. It ignores, word ordering, just does word frequency. And that's something you can possibly do to classify spam, not spam. And it was even dumber than that. The first spam filters considered each of these components independently. So like it doesn't go like, how often is the co-occurrence of king and queen? It's just how many times king multiplied by the probability of how many times queen. And that was enough to go from every second email spam to almost none of spam. Bit of history of computing. Make sense? So it's trivial, but that's like the lowest order. And this thing of like, how do you not ignore word ordering for arbitrarily length input strings is like basically what you're seeing come up in ChatGPT and things like that at the moment. Like, what's a sensible way of actually doing that encoding so that you can come up with a probabilistic model of what's the next word in the sentence? That's basically what they're trying to do. Bit sideways, but you've seen ASCII, you've seen a dictionary. I'll talk more about dictionaries. Seen a basic, this is that, I've just talked about it, but you can imagine doing it yourself of going like, if I wanted to make a spam filter, this is a really easy way to do it. It's a really easy way to classify documents and it's super fast as well, which is important. So if you just want to do like a hierarchy of filtering, you can do like, oh yeah, we'll just do this thing to cut the obvious cases. Like if like a pathological example would be, if I got an email and every word was the same word, what's the chance that's a useful email? It's like 0, right? So you're pretty safe to chuck that one in the bin straight away. Okay, questions on that bit? Unit 1 done? No, cool, I'll go on. Okay, yay. Unit 1's done. Okay, let's take a drink. Okay. So you're all experts now on the basic syntax. True. Don't expect that at all. Really bit is, this is like really interesting in terms of not the application, but the method. So all these courses, everyone has the same problem of like, we teach you sorting, but I don't care about sorting. Sorting is kind of like a solved problem. It's more about how you think about how these things scale. So I've given you hints coming up to here that you may or may not have noticed of like, the big one is I sort of just said it like, we do this integer addition and it's linear in the size of the input buffer. Like if you've got an array of ints and you do this ripple ladder, I showed you in code, it's linear in that. Like if you're going to do the primary school algorithm for multiplication, it's n squared, right? Like you're going to go carry the one, carry the one, add. So that one's, no, it's not so bad. If it's like, it's a fixed size bits, like, you know, if it's an int 64, that's not actually bad, but we talked about big ints where they can get big really, really quickly. So like if you're trying to do multiplication and it's n squared, it gets really slow really, really quickly. So is there a quicker way to do multiplication becomes really, really important really quickly. Sorting is like it's a really easy one to show that this is like, you get this scaling behavior and how big a difference it makes for simple problems. So sorting is kind of like, yeah, that's sorting. Next stuff I'm going to do some, I'll talk a little bit more about more data types that are useful. I'll talk about dictionaries and arrays, how they're laid out in memory. Some of the funkiness we're going to get with access patterns, like the particular way it's laid out in memory will affect performance, which is something you actually need to think about that you shouldn't need to think about, but every language has this problem. So I like to show that. And then we're going to go, this is the one I'm happy to move forward if people are struggling, because I know it's a bit of a learning curve, is dealing with Git, GitHub, and basic like IDE stuff. Like everyone's working in a notebook now, I'm guessing. Everyone's working in a notebook. Anyone using an editor, like a code editor? Is anyone using it? What are you using? VS Code. It's like the default at the moment. So I'll just talk about that. Yeah, like I said, I'd never actually use notebooks myself. I think they're a plague. I think, but I hope less people use them, but I'm in like an old man ship that sailed. I'm like one of those people self-publishing things. Nobody's going to listen to me. Yeah, so, but basically my work pattern is I use a code editor like VS Code, and I use the REPL, and I'll import stuff into my code session, and I debug it that way. That's how I do development every day. And we're going to talk a bit about Unix command line. So some of you have never seen a terminal before, and you're starting to use terminal stuff. It's really useful for chaining programs together. I think it's actually interesting because it'll give you a hint about how to write good code. There's this thing called the Unix philosophy about you do little things that do one thing and they do it well, and you chain those together. Then that's kind of like a really, really good pattern for software development. It's like, it doesn't make sense now because you're just writing little scripts, but it will make more sense as things get more complicated. Cool. That's where we're going. So as I said, like if anyone's like never seen Git before and they're having a fight with Git, that's normal, and you'll learn to just embrace the pain. But I can show you some hints about using it. It's fine. It's a hard learning curve. It's like, I kind of think Git's not very user-friendly. I don't want to say it's like bad. It is really useful for what it is, but I completely understand the learning curve is hard, and some of you are going to struggle if you've never used it before. Has anyone not used it before? Anyone used it before? Yeah, it's not so bad. It can get really bad, but you're never lost. It's a little bit weird. So if you just come and talk to me or send me a message, like if you want to push that stuff earlier in the lectures so you get a bit more experience, that's fine. Okay, just want to say it. Okay, but starting with sorting and analysis of algorithms. So we just showed it there. We got some random data. 1, 2, 3, 4, 5. Okay, so really common thing you're going to want to do is you're going to want to sort data. So sort data, cool. That's made a thing. So I was basically sorted before I started because I'm not very clever. Let's put some stuff in there. Okay, sort data. So data itself is unchanged. This output Y is the sorted thing. So this, I think there was a question in the first lecture of like someone who's really onto it said like, what's this little exclamation mark mean? It's not enforced in Julia in the syntax, but it's like a thing that's recommended that if you're mutating the data under someone's feet, you put an exclamation mark in there. So the difference between me going sort data So I do sort data. If I look at data, data itself is unchanged. This is a built-in function into Julia. If I do sort exclamation mark, I expect that data will be changed underneath my feet. It won't be the same data anymore. So I go sort data. If I look at data, it's sorted too. Make sense? Yep. Things can mutate. It's like the worst thing is someone who writes one and doesn't give you the hint with the exclamation mark, because they can do that too. Or even the worst case is you write something that's mutating something under your feet and you don't realize it because you haven't quite learned what you're doing. That will happen to some of you. So it's one of these things to watch for. So with scoping of variables, some operations, whether you do a copy or whether you're passing the variable around, we'll talk about this in arrays a little bit, like something to watch for. So this is useful though, because memory on a computer is finite. Like you will run out of memory. My most common crash I still get these days is I run out of memory, especially when I'm prototyping new code. It's really, really easy to accidentally allocate too much stuff and the computer runs out of memory and the out of memory killer just goes boom, no, and the program's dead. That's okay. When you guys are doing this, especially if first time developing, it's like your computer might be set up to do a thing called swapping, where if you try and allocate too much memory, it'll actually start writing it to disk. That's kind of bad if it's doing that, because you'll notice everything goes chug, 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 chug. And depending on the system you're on, I'm on Linux, as I said, so I can talk to almost no one in the room. There's this thing called top, is a memory profiling, is a performance profiling thing. So all the programs that are running on my computer will be here. See, this top one here is Zoom. It's using 50% of my CPU, sometimes over 100%. My computer has multiple cores. That's why I can do that. It'll say it's using 7% of my memory. If I do Shift M, no, sorry. If I do M, I can see, oh, cool. This is how much memory I'm using versus how much I have on this computer, 16 gig. This is my swap. So it'll be, I want to say the right thing in Windows. There's a version of this for every operating system. You'll be able to see like a system monitor or something, I think it's called. You'll be able to see how much memory you're using. Sometimes if you write a script and you go like, is it doing something or is it dead? It's good to look at this and see if the memory's full, or if the CPU's dropped off to 0. If it's still running, CPUs have dropped off. It's like, no, you've done something bad, kill it, start again. Because it can be really hard to tell how much memory you're using. So little plug for using Linux in development, because it's kind of easier to do this stuff. That's top. Don't know if I have H top. It's like a pretty top. I don't have it. I used to have it. Cool. Just a hint, because it's like, I don't know why I'm saying this now, but it'll be useful for when you're debugging stuff. It's good to know some tools. Cool, sorting. So that seems straightforward. Just remember this guy. It's like the slang for that is a foot gun in programming. It's like it's a thing where you're going to shoot yourself in the foot. Watch out for things mutating under your feet. So sort, we'll do that. If we want a hint about what sort is doing, we can go to the thing. There's this complicated thing. It's like, oh, this is strange. It kind of looks like there's an optional argument for which algorithm do you want to use for sorting. Like, that's a bit weird, but you might want to use this. Maybe this should be a hint, I guess, that they've not settled on the best algorithm for sorting. It actually kind of depends on the application. So stuff about asymptotics, but some algorithms are better for certain problems. It's like, this isn't a solved problem. It actually depends on the distribution of your data. In the, again, trivial case, what happens if your data all contains the same value? Like, which sorting algorithm should you use? You shouldn't use one. It's already sorted. So if you know something about your data, you might do something different. This one's kind of interesting. I'll use this a bit later to introduce types. There's a less than operator. So like, what do you sort by? So depending, this might seem a little bit weird now, but for different problems, you might want to sort differently. Like the type, what this thing is bigger than this thing, actually depends on the type of the data you're talking about. So like for strings, for example, for the integers of real numbers, like less than is well defined, right? What is it for strings? Like if I've got a string that's like, and you can guarantee this is implemented, if I go hello, is hello less than bacon? Julia will have an opinion on this. No, it is not. Bacon is greater than hello. That's a lexical sort. So it's just basically sorting on alphabetical order of the arrival of characters. But that's what less than means in the context of strings for Julia as a default. So you got different strings that have a different meaning for your application. You might want to do it differently. Like you might want to go sort by the shortest first name, say. Sort by the longest first name. Sort in alphabetical order of their surname. Sort by blah, 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 blah. You can imagine 100 different ways to do it. That's why this overload of like, I can pass it a function for less than for my type becomes important. Cool. I don't know if there's much else to say there. Rev, actually, I use this by all the time, this rev, because I nearly always want sort in descending order. So like if I go sort, nearly every time it's like sort goes from lowest to highest. In my job, I'm nearly always sorting by probabilities. I want the highest to lowest. I don't want the lowest to highest. So I want rev equals true. So you can do this sort. And again, there'll be an in-place version. In place means I'm editing the vector I'm putting in, editing the array that's coming in. So I want to do that. Cool. So we've got 5 minutes left, I would say. This is the devil. I do not want anyone to implement bubble sort, but here we implement bubble sort. Like bubble sort, I guess it's the easiest sorting algorithm that makes sense, but is it the most efficient one? I'll just go through this. Like anyone, like how would you sort if you didn't have any? Has anyone done sorting in another course before? You don't get an opinion. And anyone who's not done sorting before? Is this new? Yeah. Like how would you think to implement sorting? Like you're lost. Okay. So this is what I would come up with, right? So what we're going to do, I'll just talk through the code. That's fine. It's an educational point. So I just want to reiterate that. It's like if you go out and there's a job interview and they say, hey, implement a sorting algorithm and you bust out bubble sort. No. Don't do it. It's like bubble sort is bad, but it's good for education because it's really easy to see the complexity of sorting. So what you're going to do is we're going to go through, this is an in-place version. So we've got this exclamation mark that we're going like, hey, we're going to edit A. What we're going to do is we're going to swoop through the array from start to the end, and then we're going to swoop through again. And if we find any two pairs that are out of order, we're going to switch them. So that's what this line is. It's like, if the jth one is bigger than the jth plus 1, we're going to turn the jth one into the jth plus 1 and the jth plus 1 into the jth. You can do these both in one line. It's a kind of a weird syntax, but you've got this awkward thing of like, I've got to swap these things and I'm doing it in place. So I've got to get that one, put it somewhere and then put it somewhere else. This is a nice bit of syntax so you don't have to do that. It's a little bit more confusing to look at, but basically that's the idea. I'm going to go through my array from 1 to 84 in that sorted data. And I'm going to go, if I find any two that are out of order, swap them. And you're sweeping through twice because that's the maximum amount of comparisons you're ever going to have to do. That's the most amount of swaps you're ever going to have to do. So you go through this thing twice. Is that clear? Basically, I think this is one, because we're getting towards the end of the lecture. I think I'd recommend this one of going through this and just checking what it does at every step. You can see, maybe we can do that really quickly. I'll see if I can hack at it. So I'm going to put in @info. It'll show every time it finds two that are out of order. We'll just show. Okay, so A equals 1, 3, 2. Bubble sort A. Oh. Bubble sort. Bubble sort. So it went through. I probably want to show the iterators too. Sorry. Info. All right, I'm just doing this really nasty, so I can do it quickly for you guys now. J equals J. I don't want that, sorry. Okay, so it's in place. So we want to do that again. Let's reset this guy. What I've done here is I've just put in some logging that will show these are the iterations. You're going to go from I equals 1 to blah. It'll swoop through. So I equals 1, J equals 1, A equals blah. Didn't do anything. I equals 1, J equals 2, A equals 1, 3, 2. So we're going to compare 3 and 1. It's going, hey, these guys are out of order. I'm going to swap their places. Then I'm going to go again through 2, blah, blah, blah. It's already sorted, done. So basically this thing of you swoop through the array once, you swoop through the array twice. If you find any pair that are out of order, swap them and just keep going through until you've sort of done these waves of swappings, and then you get to the point where there's nothing left to swap anymore, and then you're done. That's called bubble sort, because you can kind of imagine there's lots of, you'll see a million cool out, maybe the Wikipedia one has it there. See an animation. Oh, I think there's cooler animations. I'll try and find some for tomorrow night. But you go through, if you find a pair out of place, they're not out of place, or they're out of place, so we're going to swap them. 6, 1, they're not out of place, so you're not going to do anything. That's fine. Oh no, 1, 6, sorry. Which way are they sorting? So these ones aren't out of order. 6 is less than 8, so you don't do anything. 7's less than 8, so we're going to swap their places. 2's less than 8, so we're going to swap their places again. And then 8's less than 4, so we'll swap their places again. And then we've got to go through it again, because that's not enough. So we've got to swoop through this array again, because it's not yet sorted. We'll do it again. This is why you have to do it. You have to do these 2 loops through the array. They're swapped until you can guarantee that they're not, there's no more to swap. So basically, that's the deal. So a little bit about timing, but I'm just going to jump straight to the throat of this thing and go like about asymptotics. Is like, if we have an array of length n, how many times, like you probably won't have much intuition about this yet, but which bit of this code is going to be the slow part of this code? If we look at this. Like, yep. So, yep. Yeah, because it's the biggest, you're looping, there's more stuff going on in here. If I was going to count like function evaluations, where is the function evaluation stuff happening in this code? I'd say it's like this bit. We're going to go, I'm going to compare these 2 elements of the array, and then I'm going to do some reassignment. So like if you think about this bit is the bit, the kind of the only bit that's doing real work, is what we're going to do, compare 2 values, swap them. That's the real bit of work. So how many times does this bit of code happen if this guy is length A? Order. Anyone want to guess?
Since there's 2 polars, I would guess it's quadratic.
It's quadratic, that's right. So bubble sort is quadratic. That's the takeaway we're going to get to today, because you've just got these 2 for loops. You're going to go for I and 1 to n, blah, 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 blah. If we just counted how many times this inner loop happens, and we can see how this thing scales with the size of the input. Because you can imagine the true values bubbling up through. I think is pretty much the metaphor, the extended metaphor. I didn't come up with it. It's not mine. It'd be like crap sort if I come up with it. It's terrible. Yeah, so don't use this, but you can see like this is the thing I'm trying to say is like this, maybe it's not obvious, but this bit is the slow part of the code. And you're going to swoop through it and swoop through it again. I'll do this in the next lecture, but like basically if you put a counter on there and you just count up how many times am I calling this slow bit, it scales with the square of the size of the array. The question is, do you think that's the best you can do? Can you do better than n squared? What does everyone think? Well, I'll give you there's a trivial extension to this version of it where we can go like, what happens if I swoop through this array and I didn't do any swaps? What does that mean about the initial array? Like if everything was less than the thing before it when I started, it's already sorted. So I may as well just stop then. So I can have a Boolean thing where I go like, did swaps equals false. And if it's still false after the first swoop through, you may as well stop because it's already sorted and you can stop. So there's something about the distribution of the data that you're putting into the function that says like, well, the worst case complexity for this thing is n squared, but if it was already sorted, I can kind of stop and I don't need to do it anymore. So it's different guarantees about like average case, worst case, best case for these algorithms. That's probably a good time to stop if everyone's happy with that. Thank you for your time.